Okay, let's do one more example of a mixing problem. A brine solution of salt flows at a constant rate of 6 liters per minute into a large tank that initially held 50 liters of brine solution, in which was dissolved zero point 0.5 kilograms of salt. The solution inside the tank is kept well stirred and flows out of the tank at the same rate. If the concentration of salt in the brine entering the tank is 0.05 kilograms per liter, determine the mass of salt in the tank after T minutes. When will the concentration of the salt in the tank reach 0.03 kilograms per liter? So, in the previous two examples, we had the advantage of having a little picture where everything was um, neatly illustrated. And so a good idea is to um, draw your own little picture so that you can fill in the information that's in the text. So I can't really draw on these tablets just yet, so I have imported that picture, or I'll import it here from something that I wrote with pen and paper. So this right here is an illustration of what is going on in this problem. So the solution flows into the tank at 6 liters per minute. That is what we have here. The tank initially held 50 liters of brine solution. So the initial volume was 50, but in fact, we can say a little bit more that the volume will stay constant at 50 because um, the solution flows out of the tank at the same rate. So that's also 6 liters per minute. So we know that the volume at any given time is 50 liters. And then initially there was 0.5 kilograms of salt. So x of 0 is 0.5. And then what is the concentration of the solution that's leaving the tank? Well, concentration is amount over volume. So amount is x of t, and then we divide that by 50. So I'm going to do this a little bit faster than I did the other ones because we've already done two of these examples. But our differential equation becomes dx dt equals the input flow rate, which is 6, times the input concentration, which is 0.05. So that's our total input rate. And then the output rate that we have to subtract is 6 times x of t over 50. Okay, and if we simplify that a little bit, we get that dx dt, and let me bring this to the other side. 6 over 50 is 0.12, so I have dx dt plus 0.12x equals 0.3. That's the 6 times 0.05. So again, we could treat this as a separable equation and just do it as we did example 1, but I'll show you how to do this as a linear differential equation now. And so, and then you can just see what is your preference. So this is our p of x, this is our q of x. And because we're treating this as a linear equation, we're going to do our different steps. So step 1, this is already our standard equation or standard form. The second step is we're going to use mu of t is e to the power antiderivative of, oops, and these should be p of t and q of t, because x is our independent or is our dependent variable and t is our independent variable. So that's p of t and q of t. So mu of t is e to the power integral of pt dt. That's our second step. And what we get is that mu of t is e to the power antiderivative of 0.12, and that's e to the power 0.12t. Okay, and then we're going to plug that into the solution, and the solution is x of t equals 1 over mu of t times the integral of mu of t times q of t dt plus a constant of integration. And so what we get is that x of t is 1 over e to the power 0.12t times the integral mu is e to the power 0.12t. Q of t is 0.3, so that's times 0.3 dt plus c. And the first part we can write as e to the power negative 0.12t. Antiderivative of e to the power 0.12t is going to be e to the power 0.12t divided by 0.12. And then we still have that multiplied by 0.3. That's just a constant multiple, and then we have plus c. So when you then multiply this out, these two cancel each other out, because when you multiply these e to the powers, you add the powers, so that's e to the power 0, which is 1. And so the 1 over 0.12 times 0.3, that will give us 2.5, and then plus c times e to the power negative 0.12t. And then we're going to use our initial condition. Let's just use purple here. Initial condition is that x of 0 equals 0.5. And when we put that into our formula that we have for x of t, we get that 2.5 plus c times e to the power negative 0.12 times 0 equals 0.5. Right? Our x is 0.5 and our t is 0. And what we then get is that C is equal to -2. Right? So our formula, or this is 1, and then we get 2.5 plus C is that. So we get that C equals -2. And the formula for the amount of salt is 2.5 minus 2 times e to the power negative 0.12 t. So that's an important result. That's answering one of the questions, right? Determine the mass of salt in a tank after t minutes. And then when will the concentration of the salt in a tank reach 0.03 kilograms per liter? So we now want to figure out what is happening to the concentration. So concentration equals 0.03. Well, concentration is x of t over v of t. That's 0.03. Our x of t is this formula right here. So that's 2.5 minus 2 times e to the power negative 12t, negative 0.12t, over v of t. We found that the volume was constant, equal to 50 is 0.03. And I'll leave it up to you to double check that t is equal to negative ln of 0.5 over 0.12, which is approximately equal to 5.78 minutes. And that's our final answer.